Evet, bu da olmuş. Şimdi tek sorun benim sesim duyuluyor. Evet. Evet. Bravo. Çok şükür bir sıkıntı olmadan bu noktaya kadar geldik. Niye bu kadar az hızlı gençler ya? Evet, geçen hafta da 12 kişi mi katıldı derse? Zoom'da şu soru var. Speaker, headphones değil, hayır. Ses sistem. Mikrofon duyuluyor. Çünkü şeyde de duyuldu. Stop share yaparsam mikrofonum duyuluyor mu? Hayır, duyulmuyor. Neden? Mikrofon bu mu acaba? Mikrofon yok, duyulmuyor. Aa, duyuldu. Tamam, süper. Evet efendim. Gördüğünüz gibi ve öğrencilerimiz arasında COVID olanların, aşırı COVID olanların miktarları bu aralar ciddi arttı. Umarım sizin aranızda olmaz. Yani şu çok şey. Birazcık daha rahatlaştık. Kolay gelsin. Zaten çok şükür kaloriferleri yapmaya başlamışlar. Genelde keyfiniz nasıl? Valla benimki buraya gelince iyi oluyor. Yüzde ders vermek güzel bir şey. Sizleri görmek güzel bir şey. En azından böyle ufak da olsa bir göz kontağı oluyor. Ben ekrana bakmaktan 1,5 yıl kusmak üzere. Gerçekten kusmak üzere. Ama tabii İstanbul trafiği bu kadar yükü üstümde yanımda getirmek olmuyor. Biraz sıkıntılı olabiliyor. Geçen haftayı hatırlıyor muyuz? 4 oldu. Evet, o zaman ufak bir hatırlatma için, all right. People think that we would like to have a little reminder of what we did last week. So that means I'm going to show you a video. And
in this video, we're going to focus on...
Stop. Okay.
In this video, we're going to focus
Stop.
on...
Allah. Allah. Okay. Oh, share sound'u yapmadım değil mi? Tabii bunun kendi kendine ortalığa atmasını, share sound, optimize for video clip. Okay. Now I hope the Zoom people can see this. There's only 5 of you. Do you see it?
Yes, we can see it.
Herhalde görüyorlardır değil mi? Başlayalım mı? Başladık. Okay, here we go.
On bipolar junction trans, as well as the common emitter configuration of BJ fires. So let's start with the picture. This is an NPN transistor from a P-to-P transistor. The arrow points away from it. This is the base. Now, the NPN transistor. It's going to cause a larger current to flow. Sum of the base current and the emitter current, is equal to the emitter current. E is the sum of I. Beta is so let's say that beta is if we have a base current of electron flow is actually in the opposite direction. Base current is 1 milliamp. What is the collector current? Collector current is going to be 100 times greater than the base milliamps. So beta, if beta was 200, the collector base current. And so in this way, you could use a very small current to be the sum of the base current and the collector resistor. So notice that the arrow towards the emitter of the PNP transistor. Now, the base current flows the transistor. In the NPN transistor, the base current transistor, that is conventional current from the transistor. So the collector current and the base current, the sum of the base current. Here's another example. Let's say that beta is 200. Go ahead and calculate the collector current. And so the collector current is going to be beta 100 times 2 milliamps, which is the emitted current is going to be the sum. So that's going to be 2 milliamps which gives us a sum total of 402 that you're going to encounter when dealing with NPN and PNP. Drive here is the common emitter configuration. So this is the will be across the load resistor. The input and the output is taken from the collector. It's common to both the input and the output. Amplifier circuit. This is RC, the collector resistor. Those two resistors form a voltage divider. C AC signal to basically bypass the gain of the amplifier. That allows AC signal to pass to the output. The DC power from going into the input circuit through C1 to get to the transistor. Or the DC current that comes AC signal to pass through the circuit, which is 10 millivolts and 1 milliamp. Now, R1, R2, RC, and RE values, but AC voltage across RL. Yeah, we're going to say the current is in the circuit. And what is the current gain of the circuit? Of the output voltage divided by the input voltage. The voltage of 400 millivolts. The voltage on these numbers, the voltage gain would be 40. Gain. It's going to be the rate and the input current of the AC signal. So then the current. Now the next thing we could calculate is the power gain. Let's get this in voltage first. So we have 10 millivolts. So the power at the input is which milliwatts. So that's 0.01. Keep in mind, power is at the output. So 400 millivolts, 0.015 amps. Or at the times 10 to the minus 3 watts. So that's going to be the output power. So we have an output power of 6 milliwatts. 0.01 milliwatts. And so this, a power gain of 600, is by multiplying power is voltage times current. So 40 times 50. So this helps us to see the common emitter amplifier same range voltage gain, but it has a high. So that's one of the advantages over the common base amplifier, or the common has a high power gain. Now the emitter amplifier that I do want to discuss in this video, characteristics of this amplifier. I know that looks like this. A nice sine. You're also going to get a sine wave, but it's going to be inverted. But the amplitude is larger because it's been the common emitter amplifier. So when dealing with a sine wave, it looks like. That's basically it for this video. Hopefully it gave you a and how basic BJT amplifiers.
Now, this video is slightly different than what we did last week, because what we did last week, and I'm going to put the link to this video to the chat.
You know the difference between an NPN transistor
No,
and a PNP transistor?
Stop. Okay. So last week when we did it, and I have to show you what we did last week. Slides. Okay. This week's slides. All right, now I'm sharing this week's slides, and it will have a little bit of reminder of last week. So here we go. It's already the 9th week of classes. There were questions about whether I read all papers. Unfortunately, I was gone for the break week. I didn't take all of the exams with me. And it ended up, instead of staying 1 week away, because of the weather, I had to stay 2 weeks. So I came back Friday and didn't really have a chance to finish them. We'll finish. My microphone. Yeah, the microphone is there. All right. So what did we do last week? And I should get, stop it. Okay. Should get my pointer. So we started with the different amplifier types. The voltage amplifier, current amplifier, and we discussed their properties, ideal properties. What is their ideal properties? Every amplifier can be regarded as a black box with an input port and an output port, no matter whether it's a voltage amplifier, transconductance, or transresistance amplifier. It has an input port, it has an output port. And an input signal is fed into this input port, and an output signal is seen or heard or monitored over a load resistor connected to the output. If we have a voltage amplifier, then it can be represented by an input resistance on which the input signal appears, and that signal is amplified, and this dependent source basically symbolizes the amplification. However, every amplifier also has an output resistance, and if it's converting something to voltage, the output resistance comes in parallel. If it's converting something to current, the output resistance comes, pardon me, if it's converting to a voltage, the output resistance comes in series. If it's converting to a current, the output resistance comes in parallel. So according to this, if we connect a load to the output, if we want whatever, for example, in this example, the current, if we want to have most of the current to flow on the load, then the load resistance or the output resistance have to have certain values. If anything is converted to a voltage and amplified, then the load comes in series. That means the load should be large enough or the output resistance should be small. Is this clear? Sort of voltage, current characteristics. So an ideal voltage amplifier should have a very high input resistance and a low or ideally zero output resistance, because we want all the amplified voltage to appear on the load. An ideal current amplifier amplifies current. So if it amplifies current, what do we expect the input resistance be, so that whatever current comes from the source, or most of it, is amplified? It has to be zero, close to short circuit, to have a large current. The output the same way. We want most of the amplified current to flow on the load. So the output resistance of that current amplifier. When we come to transconductance amplifier, transconductance means a voltage is amplified into a current, or transresistance, a current is amplified to voltage. So if the input is current, then we know from the current amplifier, the input resistance of the current amplifier should be very, very small. If the input is a voltage, we know from the voltage amplifier, the input resistance should be very, very large. When we come to the current, or when we come to the output resistances, if the output is a current, then it's by definition that the output resistance should be what? If the amplified signal is a current, we want most of that signal to flow across or through the load. That means the output resistance should be very, very large. In an analogous way, we are amplifying a current into voltage. So we want most of the amplified voltage to drop on the load. So what should it be ideally? Zero. So from here comes the different types and the ideal characteristics. I hope this is okay. You understood it, right? Yes. It was the circuit in the video. It was actually a very simplified circuit. It didn't give you any how to calculate the gain and the input and the output resistances. The video in the circuit assumed that it has a certain input voltage, input current, and a certain output voltage, output current. It was very, very simplified. Now I am going to recap what we did last week. And these are the source types, and then how to calculate input and output resistances, and that we have to have cascaded voltage amplifiers because one stage is usually not enough. And here in this cascade, this is a voltage amplifier, right? The input resistance of the first is 1 mega ohm. The source internal resistance is 100 kilo ohm. So there's a 1 to 10 difference between them. That's acceptable. So for the second stage, the source internal resistance is 1K, input resistance is 100K. So there is a 1 to 100 ratio. The output, the third stage, the output resistance is 100 ohm and load 10 ohms and load resistance 100. There's again 1 to 10 difference, which is acceptable because if you are amplifying a voltage and you have amplified it to 10 and engineering wise, you can't have everything ideal. Now that was one thing. Let's go to the other side. That had to do with the input resistance. Which is the input resistance of the net. Hundred ohms. So I hope that makes sense. Is it clear? All right, so input resistances are found looking into the amplifier. Is everybody here? Sorry, so for some reason we dropped out. Are you there? Is anyone there? Okay, good. If you are there, would you tell me where we were dropped off Zoom? Which slide did you see last? Which slide did you see last? Hiç ses yok. Ne yapayım ben? Okay, let me restart. Görüyorsunuz, teknolojinin de azizlikleri böyle. Your internet connection is unstable. What can I do? Give me a stabler one. Amplifier cascade. Okay, I think that's the point. Thank you. I'm stopping the video, and so it must have been this slide. Okay, so I guess this is the slide, right? We talked about input, output resistances, and that the input resistances are calculated looking from the input into the amplifier. The output resistance are calculated looking from the output into the amplifier. So now I derived the hybrid, I derived the hybrid parameters for small signal analysis. And in the hybrid parameters, we had one question for the input port, another question, equation for the output port. And in the first equation, the variables were IB and VCE. In the second stage, the variables were IC and HFE IB or IB. So the HFE is from the input to the output kind of hybrid parameter. Why? It amplifies the base current by HFE. VC, the HRE, and that's why it has F, the index subscript F. The HRE depends on VCE, the output voltage, and therefore it's regarded as a reverse hybrid parameter, and therefore comes the RE. If we can neglect the early voltage, which is the reason for HRE being here, then we can basically shorten the HIE to the emitter. So we have one input resistance. And if there's no other resistance connected to the emitter at AC, that's basically the input resistance of the amplifier. On the output side, here we had the sum of two voltages. On the output side, we had the sum of two currents. So that means they come in parallel. One is the current gain. The other one, again, has to do with the early voltage. But if the early voltage is large enough, this conductance is very small enough so that we can consider this open circuit. So at the end, we end up with a pi equivalent circuit that only has HIE and HFE IB. So we looked at two circuits last week. One was the common emitter. The other one was the common collector or emitter follower. And let's recapture them or remember them because the video seemed to be a little more complicated. So this is the circuit at AC and DC for large signals. Here we have VCC, the power supply, and the ground. For AC signals, this power supply is 0 because it doesn't change with time. So these two, the other ends of these two resistors are connected to ground. And remember, these are coupling and bridging capacitors or bypassing capacitors. They are short-circuited at AC, but at DC, they isolate the source and the load. And that one, that is used to increase the gain because the gain is a function of these resistors plus what the biasing conditions are. So the gain is, no, okay, as we cannot move. Hello. Oh, okay. The gain as we calculated with a small signal circuit had a minus sign, which means the input and output were at 180-degree phase difference. And it depended on RC, the small RE, which is the thermal voltage divided by the collector current, plus big capital R small e, which is whatever AC resistance is there at in here. Okay, so that's the gain. And here we see if this RE value is very small, the gain increases. And the input resistance is again HFE times that small RE, which depends on the biasing, and large RE. And the output resistance was RC. Do we remember this from last week? I hope you do. We derived this. Then we had the common collector design, and this had the input again from the base, but the output from the emitter. Hence, the collector is common between the input and the output. And we calculated the input voltage, which was, since the input is from the base, which was equal to the input resistance of the common emitter amplifier. However, when we calculated the output resistance, it was quite small, and the gain was also, interestingly, not larger than 1, but very close to 1. And that's the input resistance. If any load is connected to the emitter, that has to be taken into account in here, also in the gain. And the output resistance was, interestingly, when we did that analysis, inverse of the output resistance was the sum of two inverse resistances, which meant the output resistance is RE, or whatever is RE at AC, in parallel with the small RE plus the source resistance divided by HFE. So source resistance meaning this in this case, but if you have a previous stage, then the source resistance is going to be the output resistance of the previous stage. Right? I think we should have a little break maybe for 15 minutes and then we'll continue with the new stuff. All right? Let's continue in 10 to 15 minutes. Okay, shall we start again? Rina. I have a slightly longer video for you, and this one is about a multi-stage transistor audio amplifier circuit, so for amplification of voice. And I would share this with the class. And at some point, if it's something that we have already discussed, I will, is my, okay. I'm still not sure that optimize for video clip, share sound. All right. Okay. Here we go.
About the multi-stage transistor, two transistors. You could use more than two. More like Q1 and Q2. These are NPN, and this is the emitter pin of the transistor. But more on the concepts behind I'm familiar with are these three to allow the passage of an AC C1, C2, and C3 an audio signal. If you use
Wait. Again, I think. Oh, no, we are there. Okay. Okay. Oh, thank heavens. Okay.
just to give you some numbers, let's say that the frequency is a capacitor that's 100 microfarads. Hertz signal. But if you were schemes. And so by increasing low frequency signals, because when dealing with an these resistors are not required, but applied to each stage. Flip 3, R4, that R1 and R4, they form a voltage of input voltage. Because if the input voltage is to create distortion of the signal. You don't have to worry about adjusting R1. You can resistance of R1. Q1 may be too high. So that it doesn't create distortion. And so by having these two potentiometers, you don't have to adjust R1, R2 to make sure that volt distortion. Thus, R1 and R2 and now R3, we're going to give it a value of 5 kiloohms. The base current for Q1 doesn't have to be that. That's 10 times the value of R4. And if needed. So if the input voltage is too high, conductor resistance and RE the emitter resistance. The beta value of the circuit. The ratio, this could vary between 100 and so what to the sum of RC and RE by and let's say RE is relatively small compared to C. So based on that example, the beta if you don't take into account the other resistors, or assuming that they're to get the maximum current gain for the relative to the collector and emitter to maximize.
Some hints about audio amplifiers, and this is exactly what we do, what we solved as exercise session problem last week, but actually not we, but solved the problem. And I would like to stop the share, but if you have any questions, I would like to answer these questions first. So you realize a amplifier is made of transistors, resistors, and capacitors. Capacitors are used to either isolate input from the output or to increase gain by bypassing an emitter resistance. And that video talked about impedance. Impedance is not real resistance, but complex resistance. I guess most of you know. And it talked about the impedance of the capacitor. That means how large a resistor the capacitor is at different frequencies. And he gave the example of 10 and or 1 kilohertz and 1,000 kilohertz, and the resistance or complex resistance went down by 100-fold or so. So that's how the capacitor works. Ideally, it's open circuit at DC, shorted at AC. It's never as shorted, but if you talk about 5 ohms when compared to some kilo ohms, it's a pretty small value. All right, I'm going over to the slides again. And this is today's lecture, the common base design. So what is the common base? Emitter and common collector head from the base. If it's common base, it cannot hit the input from the base, but from one of these others. And since collector is usually that part of the transistor that collects all the signals, the emitter is where the input is applied from. So the base might be grounded. There might be a resistor that grounds the base over that resistor. We always have a load resistance or a collector resistance that's connected to the collector, and the output is from the collector. So the input is from the emitter, output is from the collector. Now, what do we expect? For example, what can the output resistance of this design be if the output is from the collector? No idea? Okay, the common collector design. Remember the common collector design, and it's in the common collector design, the output was from the emitter. Here, the output is into the emitter. So one would expect, logically, the input resistance of this amplifier be like the output resistance of the common collector design. Why? Here, the input is into the emitter. In common collector, the output was from the emitter. Instead of looking backwards into the emitter, you're looking forwards into the emitter. Will much change? These are just some of the questions. Now we'll go over to discuss this. So unfortunately, I couldn't find nice images, so I drew my own circuits. This is the total signal circuit. I apply signal over a capacitor into the emitter. I have an emitter resistance. My base is connected to ground, and I get the output from the collector. Instead of having a resistor, I could also have a current source, which would basically give the current such that if I know the emitter current and if I know the beta, the collector current is known and all the DC conditions are known. So we can either bias it with a resistor or with a current mirror. So, and I would like to use this kind of a T-type small signal circuit. Here between base and emitter is the small RE and the current IE flows through it. Between the collector and emitter is alpha IE. So if I insert this right in here, the base is going to be grounded, right? Does anyone disagree? No. Between the base and emitter, between the base and emitter will come this resistance. IE will flow through it, and then IE will flow through RE. And whatever comes here when this capacitor is shorted. Okay, let's come to this side. Between the base and the collector is this dependent source, alpha IE. So it will come here. And between alpha IE and VCC will go to ground will be RC. So the circuit will be like this. RE, let's go back. RE will come between base and the emitter, right? And then between the emitter and ground will come RE. So actually, they will come in parallel. And then comes RS, but we need to realize which way the current flows over RE. So going back over RE, it flows from the base to the emitter. So from the base, which is grounded, to the emitter. So this is alpha IE. This is that's a dependent source connected over RC to ground, and the input resistance is found that way. The resistance is found that way, and so the RI prime input resistance is whatever is the resistance over here in parallel to RE, right? Why are so many of you looking at your phones? I wonder. Anyway, it's your problem. So with a current source, with an I current source, RI, so there's no RE, will be directly RE. Without a current source, RI will be RE in parallel to that R capital E. So let's look at it that way, and let's try to find IE, which is the current that flows over here. And that's obviously IE is VBE divided by RE, or minus VEB divided by RE. That's the equation. And then we can look at VBE. What is VBE? The voltage drop over here. Well, somehow it has to do with VS and voltage in between RS and these two resistors. So basically, if I have a current source like a current mirror and there is no RE, then I can easily say IE, as it flows that way, also over RS, is basically VS divided by RE plus RS with a minus sign because it flows upward. That's this equation. Then the voltage gain is the output voltage divided by the source voltage. The output voltage is RC times alpha IE, but output voltage's polarity is from here to there. The current flows upwards. So there comes a minus sign. We can say V0 divided by IE divided by VS. That way we can find the voltage gain. Okay. V0 divided by IE is by definition what we see over here, alpha RC. So that comes here with a minus sign. IE divided by VS, that came from this equation one slide earlier. Wait. Yes. So the two minuses cancel each other out. We know alpha is very close to 1, so that we can also neglect alpha, and we are left with RC divided by RE plus RS. However, we know that RE is very, very small because it's 25 millivolts divided by the collector current. So next to RS, which might be in terms of kilo ohms, RE is only ohms. So we can also neglect this one. And so the gain can be found as RC divided by RS. All right. So if RE is much, much larger than RS, which could be sometimes the case, then the gain is found by RC divided by RE, and that's GMRC. So the current gain is basically alpha. And when we look backwards, the output resistance is RC. Okay. So now if we have an RE resistance connected to the emitter, then V0 will not change. VI actually will not change. VI is the voltage over here. So if you know IE and RE, VI is again minus RE IE. RI prime is RE, but the input resistance, the total input resistance, parallel equivalent of these two. So that there is an RE makes the input resistance probably slightly smaller. Looking at the circuit again. So the voltage gain we found from this is 1 plus RE should have been here. Sorry, but I will show you this one. So these are the voltage divider resistors, but is anything connected to here? No. The input is from the emitter, the output is from the collector. Okay. So that's the circuit. If we connect something to the base, like a voltage divider circuit, so that DC, we find the Thevenin equivalent resistance and Thevenin equivalent voltage, right? And so far, our inputs were applied from the base in, but in this case, no. So if any resistance is connected or resistor is connected to the base, oops, what happens is, why is my pointer gone? What happens is, now there is a resistor connected over here. You know that this is IE, the current IE. If we have a resistor over here, between the ground and resistor to the base will be that resistor, and IB will flow here. So there will be IB, meaning this input resistance prime in terms of the input resistances we find from the voltage drop between the input point, here it's the emitter, and ground, divided by the current that flows through it. The current is obviously IE, although it flows upwards. The current is IE. So whatever current flows on resistor connected to the base will be IB, or IE divided by HFE plus 1. Like, so then the input resistance Ri prime, looking over here, the emitter resistance and small re and Rb or RBB is going to be affected by that. So the total input resistance will be this value to Re. And because of that, the gain is also going to be affected by what is connected to the base divided by HFE. Did anyone have any problems understanding this? Or is it okay? But this is not complicated. You've seen this before. These are base divider resistors. This one. So you mean from here to that. And why do you have problems? Because it's basically what is between collector and base. There is this dependent source, right? So you put a dependent source between collector or RC and base, which is ground. What comes between the base and emitter? So the ground and emitter is that Re. So you take the whole symbolic transistor out, put this one in. Is that too complicated? Okay. Okay, I see. Okay. All right. So these are the different steps. But this, we cannot basically omit this using voltage dividers, even though the input is not fed from the base, but rather into the emitter and the output is from the collector. Because for stability reasons and for the proper biasing of base, we might need such voltage dividing resistors. Okay? Am I stuck? Nope. So now we put all these different amplifiers together. They have names like common emitter, which we know, we discussed last week. An emitter with an emitter resistance, we discussed last week, and now emitter follower or common collector we discussed last week. And common base, I have just tried to explain. So when we compare their input resistances, output resistances, voltage gains, and overall gains, there are a few interesting common things, such as whichever circuit has the output from the collector has resistance of RC. Whichever design has the input from the base, common emitter with resistance, emitter follower. No, not emitter follower, sorry. Yes, emitter follower, common collector. I'm sorry, I couldn't read the little print. So they have, except for this common base, these have inputs from the base, they have the same input resistances. And when it comes to gain formula, it's pretty much these formula that you need to use in the exam, unless we give you a specific equivalent circuit and ask you to work with that circuit and find input resistances, output resistances, and gain of one stage or several stages. What is important here? As it shows, for example, here. Oh, I don't see my, you see it? I guess not. Well, at least it's very close here, the pointer, although I cannot move that pointer. The pointer has RC parallel RL. So if we have something connected to the output of one stage, which might be the input resistance of the next stage, then in the gain formula, we have to take that into account. You see my pointer? Unfortunately, common emitter and common emitter with resistor, they pretty much have the same formula. Emitter follower, well, emitter follower is usually used as the last stage in a cascaded amplifier. The reason for this is if you have a load that's not that large, the emitter follower has a very small output resistance. So you might use 3 stages, all of them common emitter, common emitter, common emitter, but the last stage, common collector. And that way, you would basically decrease the output resistance such that most of the amplified signal will appear on the load, such as a loudspeaker or a display or something else. Any questions here? No? Okay. In that case, do you see my, no, again, it's gone. It's stuck. This is horrible. This is horrible and everything is stuck. Okay. Now we come to the differential amplifier, or the so-called AKA stands for, is known as the long-tailed pair. We have seen this at AC, and we know it's a very symmetrical circuit, 2 identical transistors manufactured on the same chip. Collectors are connected over RC to a VCC. There might be a, where is the laser pointer? Hello? There might be a current source that provides the biasing current. And the small signals are applied to the 2 bases, or a differential signal is applied between the two bases. And we can get a differential output signal between the two, in the two collectors or from one collector only. So properties are double input, double or single output, totally symmetric input and output, identical transistor. We remember the biasing. That was basically this, right? We tried to ask you a question on biasing differential amplifier, but in one of the neighboring sections, they didn't discuss it. So you can be sure that this will come in the second midterm. And I'm promising before the end of this week, I will finish grading your exam papers. Okay, again, I'm doing it with my hand writing because I didn't like things in the literature. This is the total circuit. Output 1, output 2, input 1, input 2, plus VCC minus VEE. And now I want, again, unstable. I don't know, this is hopeless. This is really hopeless. Wait a second. It tells me it's hopeless, it's going to drop, and I'm going bananas, of course. Let me see. Oh. I don't know what to say, but we have a real problem here with internet. Okay, it all disappeared, right? Did we get cut off? Guys, I cannot stand this whole thing. In the first class, there were mistakes that were due to the projector and so on. Now it's the internet. So I think we'll do a short lecture today and we'll make up for it next week somehow. I apologize because it's basically cutting me off very frequently. So next week we'll start with the differential amplifier and we'll go over what I did this week. But I would like you all to, let's see, duplicate. Okay. I would like you all to go through the slides I'm going to put onto the internet today and recall from last week and this week what we did, and next week you'll be more prepared and you wouldn't be confused, hopefully. Okay, goodbye everyone.